Welcome to the keynote talk. My name is Bruce Archambault, and I'm the general chair for the symposium. Henry Ott will be giving the keynote this morning, and I just wanted to introduce him, although I suspect that very few people here in the room have not heard of Henry or listened to some of his talks. In fact, I saw something on the website this morning that said that his books have sold over 65,000 copies of EMC books. And I'm thinking to myself, like, I didn't know there was 65,000 people doing EMC. But at least, unless he bought them all himself. So anyway, I really hesitate to try to to introduce Henry because I think he's so well known. But just a couple of key things that he has been over his career: a distinguished lecturer for the Society, the vice president for conferences. He's been involved in things for years and years and years in the Society. Of course, he's very well known for his teachings of his seminars, his writing of his books. He's sponsored or organized rather the fundamentals of EMC tutorial for the last few years. So he's very well known, and he has received a number of awards from the Society as well. So I don't think I really need to go into all these details. I think it's much more important for us to listen to what Henry has to say. So without any further ado, thanks for coming, and let's welcome Henry to the stage.
Okay, Bruce, thank you. I'd like to thank you all for inviting me to give this keynote presentation. I know the EMC symposiums used to have a keynote speech or a presentation as part of the symposium for many, many years. I think it was about 1990 or 91 that we stopped for whatever reason, and we haven't had one since. And this is the first one, I guess, since then. So I'm kind of honored to be doing it. What I'm going to talk about today is EMC past, present, and future. Kind of, how do we get here? How do we get where we are? A lot of the old timers in the audience probably know most of this, probably even better than I do. And some of the newer people probably do not. So hopefully you'll find it a little bit interesting. I'll also talk a little bit about how I got into EMC, and especially with the future thing, gaze into my hazy crystal ball and see if I can come up with some thoughts as to maybe where we're going in the future. Yeah, you don't have to, you can read that. The past, the beginnings, the 1930s and 1940s, at least as far as I'm concerned, that's as far as I look back at it. The U.S. military, one of the earliest EMC regulations I'm aware of is the U.S. military first encountered RFI problems. We called them RFI in those days. When a radio was installed in a Jeep, primarily ignition interference with an AM radio, as if anybody remembers some old cars. Okay, my first car was a 1939 Oldsmobile, so I'm sure that would have had some of that stuff in it also. And so as a result of that, the first military EMC specification was published in 1934 by the U.S. Army with respect to controlling ignition interference with AM radio, okay? And since then, of course, a proliferation of military EM standards have come out in the 1950 through 1965 period, shall we say. Each branch of the service published their own standards for whatever they thought was appropriate, whatever problems they were having. So what we had is a real proliferation of military EMC standards. And I know when I first began to get into the EMC business, and I'll talk a little bit about how that happened a little bit later, but the primary interest was with the military, with EMC. Commercial people weren't too interested in it at that point, so the military kind of did most of the earlier work on EMC issues, okay? But in 1967, the military, rightfully or wrongfully so, probably rightfully so, decided to consolidate all these different standards into one military standard, and that's referred to as the kind of ubiquitous Mil Standard 461 series, okay? And they came out with Standard 461, which listed limits, and the limits changed for different classes of equipment, submarines, aircraft, et cetera, but they're all in the one standard anyhow. And MIL Standard 462 was the test procedures, and MIL Standard 463 was definition. So what we had is one standard just with the limits, 461, and 462 with how to do it, how to do the test procedure. So a lot of people refer to that as MIL Standard 461/462. So that came that came into existence. And when I first started getting into EMC, they were the kind of the only standards more or less out there. It's kind of interesting if you think about MIL standards with respect to commercial standards that I'll talk about in a little while. The MIL standards are not legal requirements. They're contractual requirements. You don't have to meet the MIL standard. Of course, the military may say, you want to sell me an airplane, you do. So, well, that's a contract between the military and you. You don't want to sell them an airplane, you don't have to what? Meet the standards, you know. Whereas, legal standards are the speed limit on the road out there is 55 miles an hour. That applies to all of us irrespective, okay? And we can't get around it, okay? That's the legal requirement. So the MIL standards are contractual requirements and not legal obligations. And the 461 series started with revision A again in 1967 through F, which is the current version in 2012, and G should be out shortly, I guess. They're working on G right now. Now in 1999, I guess, MIL Standard 461 and 462 were merged into one document, which was just 461. So the 461 E version merged those two together. So now there's no longer 462. The test procedures and the limits are combined in the same standard for 461. And as I say, 461, when I originally put this presentation together, I had said 461G was coming along shortly, and that's the case here. One of the things they're talking about possibly being in it that is not in any of the present one is some indirect lightning tests. A lot of these changes to the standard are fairly minor, and sometimes every once in a while they throw something in that's kind of major. So you gotta keep an eye on it and see what the heck is going on there. So, okay. Well, change the subject a little bit here. Why should you be concerned about EMC? Got a bunch of people in this room, a bunch of people at this conference. Why are you all here? Okay, why are we all here? Well, probably the most, whether right or wrong, the most significant or the most important reason is to meet the requirements. You can't sell a product if you don't meet the requirements. Legal requirements, obviously, you have to meet the commercial standard. Even the military ones, you want to sell products to the military, yeah, they're not legal, but you got to meet them because that's the name of the game. So, as an EMC consultant, people call me up to help them with a problem, and 90% of the time it's because I want to meet a certain requirement. Not necessarily because I want to achieve a certain objective, but I got to meet a certain requirement, a written document. So how can I meet MIL Standard 461, or how can I meet FCC or European Union standards for commercial products, et cetera. Of course, the other reason to worry about EMC is to keep your customer happy. If they have interference problems, cause interference, get into a lot of trouble, they're not going to be happy with your product. So conceptually, whether there was a standard or not, maybe if you're a good corporation, you want to say, maybe I better worry about these things just so that my customers are happy and they continue to buy my product. So that's a very important reason to worry about EMC. The other thing is EMC problems can sometimes have serious or hazardous consequences. I got a couple examples just to throw out because a lot of people say, well, yeah, you got to meet them, the standards are there, but, they're just something I have to do, and is there really a fundamental reason why this is really necessary? I would throw out two examples that I'm aware of, both kind of military, naval type equipment. And that's the story of the USS Forestall and the British ship, the HMS Sheffield. In 1967, during the Vietnam War, the Forestall had a big fire on it that killed, 130 some odd sailors and airmen. investigation that sort of what it was a whole bunch of aircraft, of course, sitting on a deck waiting to take off. And for whatever reason, the radar on one aircraft scanned across another aircraft, and due to an improperly terminated connector, the radar signal coupled into the signal and fired a missile off the aircraft. Not good to fire a missile sitting on a deck of an aircraft carrier with other aircraft all around you, okay? And that hit an external fuel tank on another aircraft. Worst situation, okay? And tremendous fire. I'd say 134 people were killed because somebody didn't terminate a connector right. Or whether it was the design or the build on that one, I don't know that much detail. But the point was, here's a case where loss of life, et cetera, so because of an EMC problem. So it can be more than a nuisance sometimes, EMC to us. The other one I like to tell a story of is the HMS Sheffield. If anybody remembers back in 1982, the Falkland Islands War, the Sheffield was sunk by an Argentine aircraft. Now, this was an interesting story of an EMC problem plus coincidence, okay? The way the British fleet communicated with the homeland, which was quite a ways away from Argentina, was via satellite communication. And the Sheffield had either information to send or receive, I don't know. So they wanted to communicate back to Great Britain. And there's a compatibility problem on this ship that the radar interfered with their satellite communications. So during the period of time that they were going to communicate with Britain, they turned the radar off. As Murphy's Law would have things, just about that time, an Argentine fighter comes out to the fleet, okay? And with all the electronic countermeasures that exist on aircraft today, he knew that he was not detected on radar. So he's to launch a torpedo at the ship. But since he knew he was not detected at radar, instead of launching it, I don't know, 30 miles out or whatever the range is, he came in extremely close to the ship. Because nobody sees me, he's got no radar, he feels safe, he comes in extremely close to the ship. Launches a torpedo very close to the ship. Torpedo hits the ship and it's a dud, it does not go off. But with all the fuel it has in its tank, because it hasn't used the fuel because he launched it so close, the fuel set the ship on fire. So a dud torpedo sunk the ship. So it starts with an EMC problem and then this crazy coincidence. If he had launched it way back where he normally would have, it probably would have just put a dent in the hull, and that would have been the end of it because it wouldn't, would have burned most of that fuel. The Sheffield also had an aluminum deck, and if you get aluminum hot enough, aluminum will burn. And you put the whole thing together, and it turned out to be a disaster again with loss of life. So sometimes these EMC problems can be very, very serious. I know most of us just luckily don't have problems that serious, but they can be under some circumstances. So we have to worry about that. Okay, so let me say a few words about, as we're all aware, and a lot of us are members of the IEEE EMC Society. How did we get here, the society? How did the society get formed and the EMC part of it? Well, way back in the early days, before IEEE even existed, there were two electrical engineering professional societies. There was the IRE, the Institute of Radio Engineers, and the AIE, American Institute of Electrical Engineers. Pretty much, the IRE talked about high-frequency stuff, radio, that kind of stuff. AIE, back in the 40s and the 50s, in those days, talked about low-frequency stuff, power distribution, things like that. And they kind of were separate society. We didn't have all the digital logic and everything that fills in, wireless stuff and everything that fills in between today. So we had the high-frequency RF people and the lower-frequency, mostly power people. And in 1957, a group of military engineers out in Los Angeles got together and thought, gee, we should have something to deal with a lot of these EMC problems. And similarly, a group of engineers in New Jersey at Fort Monmouth, Army engineers at Fort Monmouth, had the same idea, okay? And they petitioned the IRE to form a professional group on radio frequency interference. So that was really the beginning of the EMC Society, was the IRE professional group on radio. And of course, we didn't call it EMC back there. they were worried about high frequency effects, radio frequency interference. So that was the beginning of the EMC Society. In 1963, the IRE and the IEEE merged into the IEEE, and at that point, the group on radio frequency interference got renamed the EMC Society under the IEEE banner. So that's kind of the history of where we came from as a society, and we've been going ever since, doing these conferences, got a lot of attendance, have been very successful at it. So, all right, we talked about some military regulations. What about commercial regulations? I'll talk about some early EMC standards that were out there, and then break it into a couple of categories. The FCC and Industry Canada, which they often refer to as the North American standards, the European Union standards, and then the rest of the world that has standards. So I say on this slide, I say early EMC standards. One of the earliest ones were the German VDE standards after World War II. The Germans put standards on commercial type products, EMC related standards. The other one that I list here, although not an early standard because it didn't come about until 1985, the VCCI Japanese standard. I list here, but for lack of another place, it's important to list it and talk about it, and I really didn't have another specific place to put it, so I kind of put it here. These were kind of voluntary Japanese, that still exists, and for EMC, for commercial type product, okay? One of the very interesting things I find in that standard was that it talked about margin and actually gave numbers. It said you should have 2 dB margin for conducted emission, 3 dB for radiated emission. I think most of us today think those numbers are not big enough, but the point was it at least addressed the issue of what? Of margin. The other standards truly, well, if you pass, you pass, you know, and as long as you pass, you're okay. As long as you keep on passing, you're okay. So we always get into this discussion of how much margin does a person need, you know. How comfortable do you want to feel is one thing has to do with that. But the VCCI standard did at least address the issue of margin a little bit and brought up, well, maybe this is an important thing that we should be concerned with, okay? Then came along the FCC regulations. Of course, I remember that very well because I was very much involved in working into EMC issues at that point. A little background on that. In the 60s, in the United States, the FCC had this, what I like to call the CB radio fiasco, where CB radio was interfering with home entertainment equipment. And this drove the FCC crazy with complaints. And the FCC, like a lot of other government organizations, don't like complaints, and I don't kind of blame them for that. So they were not happy with the CB radio situation. Now, if you think about this, the CB radio situation was kind of the perfect storm. It was a confluence of two things just happening to come together at the same time. Had they not kind of come together at the same time, it probably wouldn't have been such a disaster. And what these two things were was, first of all, the FCC approved citizen band radio, which was a low power but unlicensed, you know, you didn't have to apply for a radio license, radio service that somebody could use. And in particular, the truckers and a lot of other people picked up on this as a simple thing to communicate with each other, et cetera. So we got this tremendous increase in the use of CB radio, okay? Which is probably what the FCC intended to people to use this thing. But the 60s was also just when we were going from vacuum tube technology to solid state devices. You remember stereo amplifiers? You could cook your breakfast on top of the stereo amplifier with the vacuum tube and the heated generator. And then we're just converting these things to solid state. I remember my first stereo amplifier. I remember the tubes glowing in it and everything. We're just converting to solid state devices. Now, vacuum tubes are very linear devices. And obviously, solid state devices use junctions. That's exactly how they work. So they're very nonlinear devices. And what happens, we get audio rectification. The RF energy gets picked up, gets rectified, or the modulation gets pulled off it. See, the RF energy wouldn't hurt a stereo system. It's out of the bandwidth of the stereo system. Your stereo amplifier is not going to amplify 28 megahertz. Okay? But it will amplify the modulation on 28 megahertz. And since you've got an unlinear device, all these junctions, right, in our solid state, there was no problem in this stuff getting regulated. Now you got an in-band that amplified very well, and it became an issue. Okay, so that was kind of the gist of the CB radio fiasco. The FCC, I think, not wanting to have the same thing happen. The FCC foresaw that personal computers and things like that, computers were suddenly coming into the home. But computers used to be an industry, right? Big IBM, Remington Rand machines, et cetera. Nobody could afford them, personal, okay? But now that they saw that personal computers were out there and these were going to be in the home, and this is probably going to proliferate, which we know very well it has, probably well beyond what they ever expected even. So I think to avoid getting into such a problem that they had before, they said, let's come out with some, let's be proactive instead of reactive. Let's come out with some regulations before the problem exists instead of after the problem, and hence the FCC regulations on what they called in those days computing devices, okay? And that came out in 1979, okay? And it's kind of interesting. I was around then. I talk about IBM response. IBM and a bunch of other companies. Well, let me back off a little bit, I guess. The way the FCC comes out with the regulations, come out with a notice of proposed rulemaking first. It says, hey, we're planning on making a regulation to do this. And anybody that wants to, persons or companies, can comment on it. Okay, then we're going to look at all the comments, and then we're going to maybe change it, maybe not, and what? And finally come out with the rulemaking, see? So when the NPR came out, Notice of Proposed Rulemaking, AT&T and a lot of other large corporations, small corporations too, had responded with certain comments, a lot of them technical. Some of them were adopted into the final rules. They had some good technical points, you know, maybe this isn't the best way to do it, et cetera. So they got adopted into the final regulations. But I think the AT&T response was kind of interesting. AT&T response was, it shouldn't apply to us. Well, you know, think about this. AT&T, who made the rules in the telecommunication business back in those days? AT&T, right? And suddenly somebody else is trying to tell them what? You know, we'll take care of ourselves, it shouldn't apply to us. So the rule finally came out, and the interesting thing is in the definition of a computing device, it was added, comma, including telecom equipment, comma. That was the response to the AT&T, and it's still in there. The only specific piece of equipment mentioned in the definition is telecom equipment. So I think that was kind of interesting, where people gave a response that was based on good technical information or something. Quite often it was adopted or accepted if it was thought to be appropriate, but when it shouldn't apply to us pretty much, it kind of got turned around. Yeah, it does apply to you, okay? So anyhow, as the implementation of that took place in 1980, 81, according to the exact type of, when rules came out in 79, 80, 81, it was applied to different classes of equipment. And of course, the United States here, we've been living with the FCC rules for quite a few years now. They only applied to, it only included emission, did not talk about susceptibility. We'll talk more about that in a little while, okay? The rules were published in the Code of Federal Regulations, Title 47, which is the telecommunications portion of the rules, Part 15, Subpart J. Now, Part 15 of the FCC rules at that point was kind of a catch-all. Whenever somebody had something new come along that we needed some ruling from the FCC that didn't fit into like standard broadcast or telephone or something else, they threw it into Part 15. So that was, whatever we don't know what to do with, let's put it in or not that we don't know what to do, but whatever doesn't have a specific clear place in the rules, let's put it into Part 15. So it ended up Part 15, Subpart J. So the A, B, C, D, they had all those other parts in there. And Part 15 was kind of a mishmash of unrelated different things that just came up and FCC reacted to. Back in '89, the FCC decided to completely write Part 15 to kind of organize it, okay? Because there's a mishmash of all these things that had been collecting. And although the rules were originally, EMC rules were originally Subpart J, they're now in Part B. And they broke up Part 15 into intentional radiators and unintentional radiators, some kind of logical categories of equipment. And EMC, we ended up in Subpart B, which was the unintentional radiators, which is very appropriate, logical place to put it. And the word computing device, which is what they originally said they were regulating, now became digital devices, a more general term than just computing. In the beginning, they were thinking more about personal computers and things, but realizing all kinds of digital devices. And so, they define that as anything using digital techniques with a clock greater than 9 kilohertz. So that covers pretty much everything, okay? So they were kind of the FCC regulations that we're still living with today. Then the European Union decided to come along, and they put together a set of EMC regulations originally intended to be effective in 1982. But because of implementation problems and getting everything under control between all the European Union states and everything, it was delayed until 1986 before it finally became law and became a standard that we have to worry about. Now, the European unions do things a little bit different than we do over here. Not that that's right or wrong, but it's just different. So kind of our rules say, here's how you do it, here's how you measure it, et cetera. The European unions have two parts to the EMC regulations. There's the directives and standards. They have directives and standards, okay? Now, the directives, the original directive 89-336-EEC came out in 1989. It's been replaced in 2004 with the second version of it. And just this April, the 2014 version came out. So it's, the 2014 version's got a 2-year transition period, so it's not mandatory until 2016. So we're right now going between these two versions of directives. But anyhow, directive is law. Directive is mandatory, okay? But the EMC directive says a couple things very simple, basically two things important. It says a lot of other things too, but important thing. Your product should not radiate too much, and your product should not cause interference. What do they mean? They're kind of what? Pretty vague statement, right? Good statements, but pretty vague. You could interpret it almost any way you want. Not going to radiate too much. It's not going to cause interference. So, but that's the only legal thing. Now, they also come out with standards, and as I say on the slide, not mandatory, okay? The standards say, well, here's some numbers you can meet. Now, if you meet the standards, you're assumed to satisfy the directive. But you don't have to meet the standard. If you say, I satisfy the directive without meeting the standard, doing whatever I want to do, including maybe doing nothing, and that might be okay, okay? I'll say another word about that in a minute, compliance procedures. But so there are product-specific, and they have product-specific standards for different classes, computer, information technology equipment, lighting devices, home entertainment equipment, et cetera. They have very product-specific standards. Then they have generic standards. If your product doesn't fall into any of the product-specific categories, you got to meet the generic. Kind of the generic is the default. When you go through all the standards that exist, I'm not any of those things, then you fall into the generic standards. So nobody gets away free, okay? And there are basic standards that the other standards reference, like maybe test procedures and some things like that, okay? The basic standards are never, you got to meet the basic standard. They're referenced by the other standard, okay? Now, the compliance procedure, the simplest and the thing that most people use, and again, something different, is a declaration of conformity. We use self-comply. You say, look, my product meets the directive. And you sign a document pretty much that says that. That's the end of it, okay? Now, you can say, you got to say how you justify it meets the, well, I meet the directive because I meet all these standards. okay, or whatever. But you could also say that there's a second thing, a technical construction file. Say, my product is strange, and I don't have to do these numbers in the standard, and therefore I decided to do this, and give some rationale as to why you decided to do that. And I think that as long as I do that, I meet the intention of the directive. I'm not going to radiate too much. I'm not going to cause interference. I'm not going to be overly susceptible. But you have to have a competent body agree with you. And the competent bodies are appointed by the governments of the states in the European Union, often test houses. So in other words, you've got to get somebody else to agree with your arguments. If you come up with a really crazy argument, nobody's going to agree. The competent bodies are appointed by the states. If they start agreeing with crazy things, they're not going to be competent bodies anymore. If they want to stay in business, what? They're going to be kind of restrictive to you and make sure your argument makes sense or something, that this is the way to do it. Like this thing I make, we bury in the bottom of the ocean, so who cares about how much it radiates? So maybe I don't have to meet radiation standards. I mean, maybe that's an argument, and fine, okay, if a competent body goes along with it. The other thing is it covers emission and immunity. So this is the first time we had commercial standards pretty much to cover emission and immunity. The MIL standards did, I didn't specifically say that, but the MIL standards did cover emission and immunity. But this is the first time the commercial standards covered both emission and immunity. Now, what about the rest of the world? We got a lot more countries in the world besides the European Union and the US and even Japan and Canada. Many other, or maybe I should say most other countries have EMC regulations. Most of them follow or closely follow the European Union regulation. They may not be exactly the same, but they closely follow. They usually have the same or very, very similar limits as the European Union requirements. Not necessarily the US or the Canadian requirements, okay? Because the European Union requirements are based upon international standards, CISPR and IEC standards. So most of the rest of the world has adopted that. Therefore, the EU limits are probably applicable to the largest number of products, because all these other countries have adopted various modifications or things of it. So if you look at it commercially, the European Union standards are probably the most important commercial standards, because that pretty much encompasses most of all these other. You may have to test it differently. You may have to test it in country even, something like that, but the limits are usually the same or very close to the European Union limit. So they are probably the most single important standards in the world as far as I'm concerned. Is for commercial product. Of course, the MIL standards are for military. By the way, the U.S. talked about U.S. MIL standards. Most other countries have military standards copied pretty much closely the U.S. military standard. So there again, so military equipment would be MIL standard 461, and commercial equipment just in general would be the most common, would be the European Union standards. The Canadians have standards for ITE equipment, and I list the standard there, Industry Canada ES003. Canadians pretty much track the U.S. standards. So U.S. and Canada, which I call the North American standards, are different than the European Union standard. And the rest of the world follows Europe, but U.S. and Canada's got different. They're close, but they're different. Okay, so that's kind of where we are right now. That the U.S. and there's the U.S. and Canadian standards, and then there's the European Union, which pretty much includes the rest of the world. So regulatory summary. I guess what I just said is North America, U.S. and Canada is one set of standards, European Union and the rest of the world, and then the military. Then there's some product-specific ones, too, that apply to a very specific product, like avionics, DO-160, telecom, automotive, various other things. But as far as the commercials, the North American, U.S. and Canada, and the European Union are the most important standards to be aware of, et cetera. Okay, a lot of people ask me, well, how the heck did I get involved in EMC? And I even ask myself that question every once in a while, It wasn't some grandiose situation where I said, hey, this is what I'm going to do, Like a lot of us that got into it, especially in the early days, it just kind of seemed to happen, I got involved, I was a design engineer at Bell Labs, and I got involved in designing some equipment low-level analog equipment in a very sensitive, in a very noisy environment, which means I ran into a lot of interference type problems and had to learn to to deal with them in order to survive just as a design engineer. And I put Bell Labs there in 1960 and 1987. Two in particular, Project Ajax was kind of an interesting, this was kind of trial by fire. Bell Labs was doing some instrumentation for a underground nuclear detonation in Nevada. And I got involved in designing one of the experiments, okay? So we were measuring very low-level signals in the middle of a nuclear blast with the electromagnetic pulse from a nuclear blast. Now, think about it, what we actually, and actually in those days, of course, we didn't have what we have today is solid-state recording devices and everything else. We recorded a transient on oscilloscope using an oscilloscope camera, okay? So what we did, we were looking for a transient, okay? Now, we had portable oscilloscopes set up, buried in the ground, and a camera on them, and the scopes were set for a single trigger. They would only trigger once. And this got buried a month and a half before the detonation. So all we had to do was find the right 100 microseconds in the next month and a half to trigger the scope. You only could do it once, and you could not do it a second time. Once the scope triggered, it's over, okay? And so it's kind of you had to be pretty damn sure. You did everything you could possibly think about to make sure this thing was going to work, because you weren't going to get a second try. And the lab spent like $1.5 million for this experiment, okay? So the interesting is I came up with an idea of a way to trigger these things is to when to start the sweep, which is a lot of the problem. Is prior to that, most people doing instrumentation, these nuclear underground blasts, were not exceptionally successful in a lot of it, but they triggered from the detonation pulse. You know, when the pulse went to detonate the bomb, but that was a fairly long time delay, especially in the microsecond category. So it's very difficult to get that to come out right. Well, talking to the physicists, et cetera, found out that there's a neutron precursor that comes out of the nuclear device just before it really blows apart. And by going through we let the neutrons hit a piece of lead, convert it into gamma rays, and my idea was to detect the gamma rays. And that was much closer to the actual event, and therefore the time delay didn't have to be quite as accurate. So I built a gamma detector to measure this or detect this precursor and trigger off of that. It's kind of interesting that we had 6 experiments that the Bell Labs were doing there, 6 different groups. Every group was running a different experiment, and they were on their own what they wanted to do. Well, you know, I looked at this. I was a fairly young engineer at that point. So, well, if mine doesn't work, so we screw up one experiment. They probably won't hang me for that, you know. But what happened is they said, well, you got this gamma precursor. 5 of the 6 experiments decided to use my gamma precursor, or my gamma trigger. Now, of course, if it doesn't work, none of them are going to work. Not just mine, which I could accept, you know, but none of the other ones are going to work. Well, it turns out in hindsight, the only one that didn't get the data is the one that did not use it, okay? And the 5 out of 6 that did use it got the data because the trigger was correct, okay? Now, it's kind of interesting because this thing is sitting out there for, as I say, about 6 weeks before the detonation. Gamma radiation can set off this, from the atmosphere, can set off this trigger, and we can only trigger the scope once. So it's sitting there for 6 weeks. So my idea was to build a doghouse around the detector with just a little window looking where I knew, and this doghouse made out of lead bricks. The idea was to block any gamma radiation from triggering it, and only the thing we wanted. So I go to my boss at one time, I still remember this, and I forgot, I want to buy, I forgot how many, 200 lead bricks. He looks at me like, you know. He finally says, can't you use anything but lead? I said, yeah, we could use gold. And with that, he signed, didn't say a word, he just signed the purchase order for the lead bricks, okay? But it worked, and we got the data, okay? Then I was involved in a bunch of tape recorders, digital tape recorders, again, measuring very low-level signals in a very harsh environment with big motors and magnetic brakes and things, 10-inch reels of half-inch tape. So that altogether kind of, I got involved in a lot of EMC issues, okay? I knew the fella at the labs that was in charge of in-house education. Bell Labs was very big on education, in-house education. And I went to him, he's the director, and I said, you know, what we need is a class on EMC or noise and interference, whatever you want to call it, because people don't learn this in school. Now, remember, this is the 60s, okay? People don't learn this. They know what they learned in school, but they don't know, you know, they're dealing with all these noise problems that they learn nothing about. And he says, yeah. So, okay, so I left, and for 6 months, I never heard from this guy. I said, he forgot everything that I said to him. But 6 months later, I get a phone call. He said, come on up my office. Okay. I go up his office. He said, remember about 6 months ago you were in here and you were talking to me about a class on blah, 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 you know, noise and interference and things? Yeah. He said, well, I checked all our resources. Nobody knows anything about it. I said, yeah, that's why we need a class on it, you know. But being a naive young engineer, I said, well, I'll teach it. See, I knew a little more than everybody else. Not a lot more, just a little more. Okay. So I started teaching it in-house at Bell Labs, okay? And the early days of the class were kind of crude, but as we went along, it got better and better. We all learned a little bit more. As a result of that, I ended up with a big stack of notes from the class, which I said, oh, this would maybe make an interesting book, okay? And I turned that into my first book, Noise Reduction Techniques and Electronic Systems, okay? Which was the class notes from what I had taught at Bell Labs. Then in end of 1997, beginning 1998, I decided I wanted to be in the EMC business 100%, not just kind of a sidelight at Bell Labs. So I kind of left Bell Labs and went into consulting business for myself. A lot of work for the early day personal computer companies that were fighting with these EMC problems. And so I ended up doing a lot of training and consulting, and then I wrote my more recent book, 2009, Electromagnetic Compatibility Engineering. I kind of look at it, noise reduction, electronic systems is my experience at Bell Labs, and electromagnetic compatibility engineering is kind of what I've learned in my experience after I left Bell Labs. Let's talk about EMC education as long as we're, when I was looking around to find information on this, trying to deal with Project Ajax, et cetera, there wasn't much information on EMC in the literature. You learn at school, go to the library, I'll research it, right? There should be no problem. Well, you go to the library and there's nothing there. Most people learned anything about learned it from the school of hard knocks, okay? You know, just by doing it wrong and doing it. The only book that, well, there really was another one I list later on, but the one book that I found was Ralph Morrison's book, In Grounding and Shielding and Instrumentation System. I got a picture of it there. It was only a 150-page book. I still have that little red copy. It's about a 1/4 inch thick, very small book. And that was a second edition. There evidently was a first edition before that, but I still have that book on my bookshelf. I kind of honor that thing. That's where I learned as much as I could about it, because it was the only book out there. I ended up meeting Ralph Morrison years later. The other thing that was there that was some of it was useful is Armor Research Conference Proceedings, 1954 to 1964. This was really the precursor to the EMC Symposium. This was something that the military was running through the Armor Research Institute as EMC conferences. So that precursor to the start of the actual EMC Society, this conference here. And that was a good source of information. Of course, a lot of articles over a period of about 10 years there. Don White Consultants was also out with a series of books on EMC. That was the other source of books. Military-oriented, because that was the interest in EMC at the time, obviously military interested, but that was there. I still have some of those books. And that's a few miscellaneous articles and various other things. But, you know, I say the dark ages for EMC education. It really wasn't a lot there, and hence the thing is I went to Bell Labs, tried to get a class in Bell Labs to do it. No, that's kind of the past, okay? Let's talk a little bit about the present. Driving forces behind the EMC. I think there are a lot of them, but there are four major ones that drive what we're doing and what we see at this conference, et cetera. One is regulations. I said earlier, most people call up a consultant and says, help me meet the regulation. Not help me do something functional or something, but help me meet the regulations. So obviously the regulations are important. As the regulations change, that's important to us to keep up to date, okay? The other one is technology. Technology has changed tremendously, obviously, over the last 20 years. Frequencies have gone up, high speed, high scale, large scale integration, et cetera. So all these things affect what we do here very much. Signal integrity. As we get to higher and higher frequencies, the signal integrity and EMC begin to mesh and become more or less the same set. Now, even at this conference, it's code with signal integrity and power integrity. So you see these things are beginning to mesh. And the other one is this time to market. You know, when I was first working at Bell Labs, we would design something and test it to death for a couple of years before we put it on the market, okay? Today, it's got to be on the market in 3 months or 6 months or something because it's obsolete after that, you know? So things have, and EMC failures can have a big effect on time to market. I get everything done, but I can't sell it because I can't pass the EMC test. So this becomes very important to us, okay? Regulation. Manufacturers design products to meet the regulation, primarily, okay? Because they're the minimum requirements. Regulations change, design practices also have to change. Multiple testing may be required for different countries, different places where you're selling the product, et cetera. There's a lack of harmonization of standards and test procedure. You know, what would we like, or what would a manufacturer, I think, like, is one EMC standard for commercial product. It's all the same. You test it once, you pass it, you can sell it anywhere in the world. But we're not there, and we probably never will get there, okay? But that's what a lot of people would like, I think. Technology, of course, much higher frequencies. I like to say the first edition of my book, Noise Reduction Technique, frequencies were in the single-digit megahertz range at the high end. The second edition of my book came out in '88. We were in the tens of megahertz, high end. My newest book came out in 2009. We're in the hundreds of megahertz to gigahertz range. So clearly, you can see we've gone up and up and up in frequency. High-density IC packaging becoming more and more, cramming more stuff into a small chip. Okay, PCB technology, distributed capacitance for decoupling, using the planes in the board for decoupling. Micro-via technology, buried vias, blind vias, et cetera. Use of flex circuits. All these things affect what we do as EMC engineers and how we deal with it, okay? Low voltage differential signaling. A lot of people are using that. And everybody thinks, well, that's great for EMC. Well, like a lot of things, my experience is yes, the answer to that is yes and no. Yeah, it's differential, which is good. It gets a current out of the ground, et cetera. But the rise times are very fast, often in the hundreds of picoseconds. So the very fast rise times makes the EMC issues worse. The differential signaling makes the EMC issues better. Sometimes you come out ahead, sometimes you come out behind, okay? So like a lot of things, it's not just the solution to all the world's problems. More and more wireless devices. Grounding and shielding is becoming important. Heat sink grounding. Because of large-scale integration, things are getting hot. We got to put heat sinks on them. Often we don't think about grounding them, et cetera. And that's a problem. I mentioned EMC and signal integrity pretty much come together. I'd like to look at this. EMC is how your circuit or system affects other circuits or systems. Signal integrity is how your circuit or system affects itself. Does it interfere or screw up? See, they're really the same thing. But when we're talking about this affecting something else, when we're talking about it affecting yourself. And kind of if you look at it that way, I think you seem to see how these things become to go together. At high frequencies, these things merge more and more closer together. I remember in the early days when we saw higher and higher frequencies coming along, myself and a fellow working with me were thinking about how are we going to deal with these high frequencies. And we said, well, you know, some of the supercomputer manufacturers back in those days, the 70s and the 80s, or the 80s actually, must be dealing with these things So the fellow I was working with me had a friend that graduated him that worked for one of the supercomputer companies. So we called the guy up, okay? And we explained our interest in these high frequencies. And we said, you know, we've been telling our clients to do A, B, C, D, E for EMC. You know, is that a good idea? And the guy said, well, I think we asked him, do you do that? He said, no. No, you don't do that for EMC? He said, no, we do it to make it work. That they did the same thing, but what? For a different reason, for signal integrity, okay? We were doing it for EMC. That's this merging of the, but that was interesting. No, we don't do that for EMC. Yeah, I did just like you, you know, what, you don't, you know? We've been wrong all along, you know? No, we do that to make it work, okay? The other interesting thing, the last couple of bullet items, although the techniques are the same in everything, signal integrity and EMC, millivolts and microamps of noise can cause EMC problem. You normally need tens or hundreds of millivolts and milliamps to cause a signal integrity problem. In other words, they're the same phenomena, but the EMC problems occur at a lower level. So you see the EMC problems before you see the signal integrity problem. Because the signal integrity can tolerate more noise than the EMC can tolerate. Okay? Time to market, pretty much obvious, I think, to most people. And I don't have to go to too much that I got here. EMC Education, the awakening. In the late 1980s, I was chairman of the education committee of the IEEE EMC Society. And we decided to survey all the US and Canada electrical engineering universities as to whether they did anything on EMC, taught anything on EMC. And we sent out a survey. We explained what EMC was and a lot of things, okay? And out of over 300 universities, I think it was about 350 universities we sent that survey to, 6 said they did something. 6 out of 350. And it's not much better today, by the way. Maybe a little bit, but not a lot better today, okay? There were so few that said yes. I got in touch with all of those that said yes and found out. But I was curious, why did they say yes and everybody else said no? And the unifying thing there, in every one of those 6 cases, there was somebody on the faculty that had a lot of industry experience, besides just academic experience. And he or she was pushing this EMC. The most interesting comment I got from a fellow by the name of Marty Graham at University of California, Berkeley, was I got EMC into the curriculum in spite of the administration. Not with the help of the administration, in spite of the administration. Interesting comment. That was the situation in those days, okay? All right, so let's kind of look into the future. Now we're really getting out there on a limb somewhere. My hazy crystal ball. Technology. Well, more and more we're having problems with variable speed motor drives, Class D audio power amplifiers, LED lighting, things like switching devices to control things that they never used to control, okay? And we're seeing a lot. LED lighting, I'm seeing a lot of problems with radiated emission, and often people want to use LED lighting on something that's already got cabling installed for standard incandescent lighting. And the cabling and everything else was never planned for LED lighting, but nobody wants to change the cabling. Sometimes in an aircraft or a ship or something like that, the idea is just change it to LED lights, but we leave all the cabling alone just the way it was, you know, and not designing it from scratch. And that's a problem. Broadband over power line, single conductor RF transmission line, I think hopefully that's dead, at least in the US. God rest in peace. But this idea of using a single conductor transmission line to send RF energy down around the country is kind of the dumbest thing I ever heard tell of, okay? Home automation is becoming a real problem. All kinds of low voltage home automation types in, controlling the lights, controlling everything, and that's becoming more and more of a susceptibility problem. Wireless everything. Everything's becoming wireless today. So RF fields are what? All over the place. Up close, too, because you got these wireless devices close to other things. The radio transmitter is way down the street. Or, you know, but the wireless device is right next door or right next to your your product. So interesting, we have more problems with low-power wireless devices close to your product than high-power devices far away from your product, like the radio stations and things like that, okay? Wireless implanted devices, PCB issues. FR4 is a lousy dielectric at high frequency. Okay, a lot of people are finding out. You've got a lot above a gigahertz in particular, increased signal loss, which slows down the rise time, because the higher frequencies are attenuated more than the lower frequencies. The other thing we're finding is the products get smaller, lighter, and more mobile. And operating levels lower, 5-volt logic, 3-volt logic, 1.25-volt logic, 3/4-volt logic, et cetera. More and more susceptibility problems are coming up. Most of my consulting work when I left Bell Labs to do consulting was on the radiation or emission problem. Now it's equally spread between susceptibility and emission problems. So we're seeing more and more susceptibility issues coming up and susceptibility predominating things. Regulations, possibly more stringent. ESD limits in particular. I said present standards are not preventing field failures. A lot of my clients are saying, you know, they meet the ESD standard, but they're still having field failures with ESD. I got a lot of clients that were testing higher than the level specified in the standard. So, I mean, the standards may catch up or maybe not, but I'm seeing that as a big issue. Higher voltage, maybe 12 to 24, 25 volts, 1,000 volts, et cetera. Better simulation of real-world ESD events. This contact ESD testing is great and repeatable, but it's not what the real world looks like. And there's a lot of issues there I don't have time to get into. I mentioned before that the newest EMC directive came out in April 2014, just a couple of months ago, 2-year transition period. The major changes, it seems to have additional responsibility for importers that are importing stuff into the European Union to keep records, et cetera, of the compliance of these products, et cetera. We'll be doing more EMC testing above a gigahertz and the problems associated with that. The U.S. was most likely not impose susceptibility limit. Remember I said the U.S. and Canada just has emission limit. We always talk about, well, the U.S. imposed susceptibility limit. Well, one reason I say that is, first of all, we get it for free. Most products, most manufacturers want to make a product they can sell worldwide. So they meet the European Union requirements, which do include susceptibility. So why should we put susceptibility limits on? You know, if you can get it for free, what? You know, why put more regulations out there? A big thing that I strongly feel, more pre-compliance testing. We've got to teach manufacturers to do pre-compliance testing. Too many manufacturers designing a product have no idea what the EMC performance is and send it to a test house to be tested for compliance, and they fail. You know, they got to learn to do the testing, at least pre-compliance, not final testing, not accurate testing. Simple, inexpensive pre-compliant test setup today can be had for under $5,000. In some cases, as little as $3,000. Prices have come down on spectrum analyzers, lots of other things. But you got to learn how to do this, okay? I think this is very important that we see more and more manufacturers doing this. I do a lot of consulting for clients. They could fix the problem themselves if they only did some simple little preliminary tests. They wouldn't have to hire me or somebody else, okay? And this is true for both small and large manufacturers, not just small manufacturers that have this problem. Some of the big companies don't do pre-compliance testing either. So future trends, well, okay, that's where we, okay. Okay, yeah. Additional EMC regulations, international harmonization. As I said, everybody would like one set of standards. I think it's more important if we harmonize the test procedures, even than the standard. Because if everybody's test procedure was the same, you could do one test, and you can compare that result against 12 limits. That's no problem. As long as all the tests are the same, then you can do one test. If each test procedure is different, though, you have to what? You have to do a different test every time. So, you know, yes, I would like all the limits to be the same, but more important is make the test procedures the same. And you can still have a dozen limits or 100 limits, because once I do it, I can compare it against, you know, it's just looking at a chart or a table and see what I pass and what I don't pass. But the fact there's slight minor differences quite often in test procedures, that makes me do it over again, okay? Mutual recognition agreement.